Hello everyone, this is the video lecture for the topic Gaussian mixture models from the 4th unit Ensemble Techniques and Unsupervised Learning for the subject Artificial Intelligence and Machine Learning. Objectives are to learn about Gaussian mixture models and to apply this GMM models for the machine learning problems. GMM Gaussian mixture model is a soft clustering algorithm where each point probabilistically belongs to all clusters, but this is different from k-means clustering. In k-means clustering, each point belongs to only one cluster. Since it is a probabilistic model which assumes all the data points are generated from a mixture of Gaussian distributions with unknown parameters. This is a model which will make assumption based upon the probability value. The algorithm attempts to produce k Gaussian distributions that would take into account the entire training space. Every point can be associated with one or more distributions. Consequently, the deterministic factor would be the probability that each point belongs to a certain Gaussian distribution. And GMM models having real-world applications like used for signal processing, the customer churn analysis, language identification, video game industry, and the classification of songs. Expectation maximization. In GMM models, an expectation maximization method is a powerful tool for estimating the parameters for Gaussian mixture model. This EM algorithm, expectation maximization algorithm, is used in maximum likelihood estimation where the problem involves two sets of random variables of one x is observable and the other z is hidden. But in case where this is not feasible, we associate the extra hidden variables z and express the underlying model using both to maximize the likelihood of the joint distribution of x and y. So EM algorithm is an iterative method used to find the maximum likelihood estimates of parameter in a probabilistic models, where the model depends on unobserved, also called latent variables. EM alternates between performing an expectation step, which computes an expectation of the likelihood by including the latent variables as if they were observed, and maximization step, which computes the maximum likelihood estimates of the parameters by maximizing the expected likelihood found in the E step. So in the expectation step, it will find the expected values of the latent variables. In maximization step, first plug in the expected values of the latent variable in the likelihood of the augmented data, then maximize the log likelihood to re-evaluate the parameters. EM is a technique used in point estimation. Given a set of observable variables x and unknown variables z, we want to estimate parameters in a model. It is a widely used maximum likelihood estimation procedure for statistical models when the values of some of the variables in the model are not observed. It is an elegant and powerful method for finding the maximum likelihood of models with hidden variables. This algorithm in E step, the algorithm estimates the posterior distribution of the hidden variables Q given the observed data and the current parameter settings, and in the M step, the algorithm calculates the ML parameter settings with Q fixed. Generally, EM algorithm works best when the fraction of missing information is small and the dimensionality of the data is not too large. EM is useful since it has many features: conceptual simplicity, ease of implementation, and the fact that each iteration improves the performance, the value of L of theta. The rate of convergence on the first few steps is typically quite good, but can become slow as you approach the local value. It is often used in data analysis to manage missing data. It overcomes some of the limitations of other techniques such as mean substitution or regression substitution. These techniques generate biased estimates and specifically underestimate the standard errors. Expectation maximization overcomes the problem. So that's all about the topic. Thank you.